All right, let's dive into the motor revolution, going from brushed to brushless. In this story, it's really about the very heart of the machines that power, well, pretty much everything around us. We're going to trace its incredible evolution, from the old-school kind of clunky motors of the past to the super sleek, silent, and powerful ones you find in all the cool tech today, like drones and electric cars.
I mean, just think about it. From the tiny drones buzzing overhead to the electric car you might be driving, motors literally make our world move. But have you ever stopped to think about how this pretty simple machine evolved into the high-tech marvel it is today? The motor in a brand new EV is a world away from the one in your grandpa's old drill. So what happened in between? How did we make that jump? That's what we're going to dig into.
Okay, so to really get this whole revolution, we've got to go back to the very beginning, to the spark, you could say. We need to understand the basic science of how you turn pure electricity into actual physical motion.
So what is a motor, really? At its heart, it's basically an energy converter. It's a device that takes electrical energy, from a battery or a wall socket, and magically transforms it into mechanical energy, into motion. And the secret ingredient, the real magic that makes this whole trick work? It's a magnetic field.
And this right here, this is the secret sauce. This is Fleming's left-hand rule. And it shows just how perfectly these three things, a magnetic field, an electric current, and motion or force, are all interconnected. It's like a law of nature. If you've got a magnetic field and you run some electricity through it, bam, you create force. You create movement. And believe it or not, this simple, elegant principle is the foundation of literally every electric motor ever made.
All right, so with that basic physics in our back pocket, let's take a look at the OG, the classic workhorse that honestly powered the world for more than 100 years, the brushed DC motor.
So what are we looking at here? It's actually pretty simple. You've got two main parts. On the outside, there's a stationary magnet. That's called the stator. It just sits there. And on the inside, you have the part that spins, which is an electromagnet, and we call that the armature. The whole game, the entire goal is to get these two to play a game of push and pull, to keep that armature spinning round and round.
But here's the really clever part. See, if the inside electromagnet just got pulled toward the outside magnet, it would just snap into place and stop. Dead. That's no good. To keep it spinning, you need to be able to flip its magnetic poles, its north and south, at the perfect moment. And the piece of mechanical genius that pulls this off is called the commutator. The best way to think of it is as a rotary switch that's perfectly timed to reverse the current every half turn.
Okay, so that raises a question, right? How do you get electricity to a part that's constantly spinning? Well, that's where these things called brushes come in. They're just stationary blocks, usually made of carbon or graphite, that are literally pushed up against the spinning commutator. They physically make contact, scraping along to deliver a steady stream of electricity to the coils that are spinning around.
So let's put it all together. It's like this beautifully timed mechanical dance. First, power flows through those stationary brushes into the spinning commutator. That juice energizes the armature coils, turning them into an electromagnet, which gets repelled and attracted by the outside magnets, causing it to spin. But then, and this is the key, just as it's about to lock into place, the commutator rotates to a new position, which reverses the current. This flips the armature's magnetic poles, and that forces it to get pushed away and keep on spinning. It's this constant physical scraping process of push, pull, flip, and repeat. And you know what? For a very long time, this was the peak of motor technology. It worked. But that physical, scraping contact, the very thing that made the whole design so clever, turned out to be its biggest Achilles heel. Yeah, this really lays it all out. That one little point of physical contact, the brushes rubbing on the commutator, is the source of pretty much every single problem with this design. You've got wear and tear, those brushes physically grind down and you have to replace them. All that friction creates heat, which is just wasted energy. It's also noisy, you can literally hear it scraping, and all of this means the motor has a limited lifespan. That mechanical wear is a ticking clock.
So the engineers realized the solution wasn't to try and make a better brush. The solution was to get rid of the brush completely. And that led to an absolutely revolutionary redesign, the brushless DC motor, the BLDC. And here it is. This is the big flip. This is the core idea that changed everything. A brushless motor basically takes that classic design and turns it inside out. Now, the permanent magnets are on the part that spins, the rotor, and the electromagnets, the coils, are on the stationary part, the stator. It seems like a simple switch, but trust me, this one change is the key to the entire revolution.
Just look at this side by side.
It makes it so clear. On the left, you've got the classic brushed motor with the coils spinning on the inside. But on the right, you see the brushless design. It flips the whole thing. The coils are now on the outside, stationary. And think about what that means. If the electromagnets don't spin anymore, you don't need brushes or a commutator to get power to them. You can just wire them up directly. It is such an elegant and brilliant solution to the problem.
Okay, but hold on. If there's no mechanical switch, no commutator, how in the world do you switch the electricity to keep the motor spinning? Well, we simply replace the physical switch with a digital one. Every brushless motor comes with a little electronic controller. It's basically a tiny computer brain that uses electronics to fire electricity to the right coils at exactly the right moment.
So what's this little electronic brain actually doing? What's its job? It's performing what looks like a magic trick. Instead of moving the magnet, it makes the magnetic field itself rotate.
Let's walk through it. First, the controller zaps one set of coils with electricity. That creates a magnetic field, a north and a south pole. The permanent magnet on the rotor is naturally attracted to that, and it gets pulled to line up with it, right? Simple magnetism. But just as the rotor gets there, the controller instantly switches off that first set of coils and turns on the next set in the circle. Poof! The magnetic field has now jumped to a new spot, and the rotor, like it's playing a game of catch-up, gets pulled along to this new position.
Now imagine this happening hundreds or even thousands of times every second. The controller creates this seamless, rotating magnetic field, and the rotor's magnets are just constantly chasing it around in a circle. The result? You get smooth, powerful rotation with absolutely zero physical contact. That means zero friction and zero wear and tear. It's brilliant.
So, we got rid of the friction, we got rid of the flaws. That's great. But what does that actually mean in the real world? What's the big payoff for this super clever redesign?
Oh, the advantages are just massive. First off, efficiency. With way less energy loss to friction, you get longer battery life. That's huge for your drone or your electric car. They're also way more reliable and have a much longer lifespan because there are no brushes to wear out. And they're quieter, no more scraping noise. Plus, you get more power in a smaller, lighter package. And maybe best of all, since a computer is in charge, you get incredibly precise control over speed.
And really, this table kind of says it all. You'll still find brushed motors in simpler things like basic tools, pumps, or fans where high performance isn't critical. But when you look at modern, cutting-edge tech, drones, electric vehicles, the hard drive in your computer, even stuff for aerospace, it's all brushless. They absolutely depend on that efficiency and reliability.
So here's the big takeaway. The shift to brushless wasn't just a small step up. It was a leap. By swapping out those physical mechanical parts for smart electronics, we didn't just improve on an old design. We literally opened the door for a whole new generation of technology that just couldn't have existed before. When you think about it, it's just an amazing story, isn't it? We went from physical sparks and scraping parts to silent, perfectly precise, computer-controlled motion. It really makes you wonder, now that we've mastered rotation without any physical contact, what's the next big frontier for motors? What's the next barrier they're going to break?